All right. Uh, I'm giving this supplementary lecture regarding the chapter frequency response, and we will be doing some examples for the Bode plots, how to construct the Bode plots as using the table or techniques that we have seen in the class lecture. So this is the table that we had used to construct the Bode plot using some standard factors as shown here. So in during our class lecture, we had seen example 14.3 and a practice problem 14.3. Now let's see example 14.4 and let's see we can uh, do it, obtain the Bode plot or not. So here I have a transfer function h omega, and let's write it down here. All squared. So in this case, you can see that obviously this is not in standard form. So we will first transform or rearrange the terms into the standard form. Which is h omega. We take 10 common from the numerator, and we will be left with 1 plus j omega by 10 over. And we take 5 common from this pole, this factor here, and 5 squared will be 25. So we will be left with 25 j omega and 1 plus j omega over 5 whole squared. Okay. So now to get the Bode plot, we need to get the magnitude plot, we need to have HDB, which is 20 log of h omega magnitude. So this is basically now this 10 over 25 can be written as 10 over 25 here, which is the k value of k we had seen previously. So these are the 4 values, 4 factors of the h omega in standard form to plot the Bode plot. So 20 log of the magnitude of h omega will be 20 log of the magnitude of 10 over 5 is just 10 over 5. So this is basically the k plus 20 log of magnitude minus 20 log of j omega, magnitude of j omega, and minus 20 log of 1 plus j omega over 5 whole squared magnitude. Okay, so 20 log of 10 over 25, we calculate its value. So this value is coming out to be minus 7.96. That is 20 log of or it can be approximated to minus 8 dBs. All right. So we have a constant line at minus 8 dBs and we have a 0 at omega equals to 10 with a pole at crossing uh, uh, omega equals to 1 and we have repeated poles at omega equals to 5. So let's draw the horizontal and vertical axes and construct the Bode plot using these factors. So let's draw this constant line 20 log of 10 over 25, which is minus 8 dB. So I have a constant line using this table uh, uh, which is shown here. The first factor k, 20 log of k, is just a horizontal straight line. So I will write, let's suppose this is minus 8 dB here. I will just draw a horizontal line. Let's call this line number 1. Okay. And next I have a pole which is crossing at omega equals to 1. Okay, so I have a j omega in the denominator. So let's check out the table. When I have 1 over j omega n, I have a negative slope crossing omega equals to 1. So here n, capital N is 1 in this case, so I have slope will be minus 20 dB per decade. So let's say I have omega equals to 1 here. And let's say I have, this is 110, this is 100. So this negative slope will be crossing at omega equals to 1 with a rate of minus 20 dB per decade. That means at reaching omega equals to 10, the value of that slope will be reaches to minus 20 dB. That means somewhere here. So slope on the line will be like this. Okay, crossing omega equals to 1 and obviously extending further. So this is, let's call this line number 2 and its slope is minus 20 dB per decade. And obviously this was this is basically 1 over j omega, and this is you can say from the 20 log of k or minus 8 dB. Right. So these are the line 1 and 2. So next I have a 0 at omega equals to 10. Okay, this is in the numerator, so it will be a 0. That means a positive rising slope after omega equals to 10, as shown here in this case. 1 plus j omega over c have a slope like this at the rate of 20 dB per decade. Uh, this slope starts from omega equals to 10 and goes to with a rate of 20 dB per decade. That means at reaching 100, the value should reach to the 20 dB. So let's suppose I have positive 20 dB here. So this line will maybe reach up to this value here. We connect these two lines. And let's call this line number 3. And obviously for omega less than 10, its value is 0. Okay. Now I have a repeated pole at omega equals 5. So let's say I have a 5 here and maybe 50 somewhere here. So I have a pole at omega equals 5 and this factor is squared. That means the value of n is 2. So the rate will be minus 40 dB per decade. Okay. And it starts decreasing at the value of p, which is 5 in this case. 1 plus j omega over 5 whole squared will be translated on the graph and this way. Okay, so it will start decreasing after omega equals to 5, and for a decade, like from 5 to 50, it should goes to with a minus 40 dB rate. So it will, let's say I have a rate like this. So at 50, it should reach minus 40 dB. Then we can say the rate is minus 40 dB per decade. So this will go like this. This is minus 40 dB per decade. So now let's call this line number 4. And now we have plotted all the individual lines using the standard form of transfer function. And now we will add them graphically to get the final resultant transfer function. So let's look at the overall diagram. We have some transition points at omega equals to 5 and 10. Okay, at omega equals to 10, we have a 0, and at omega equals to 5, we have this repeated poles. And before omega equals to 5, or when omega is less than 5, I have this constant line, horizontal line, and this slope which is crossing omega equals to 1. So let's combine a line number this 1 and line number 2 for omega less than 5. So what we have to do is let's analyze this crossing zero crossing point. So here the value of line number 2, the value of h is 0 at omega equals to 1, whereas that for line number 1, the value is about minus 8 dBs. So when we add these 2 points, I will reach to minus 8 dB. Okay, and when we combine a horizontal line with zero slope and this uh, negative slope line with a rate of minus 20 dB, the resultant will be a line uh, of with a slope of minus 20 dB. That means this line number 2 is basically shifted here downwards due to this constant horizontal line slope. Okay, and also the its slope will be minus 20 dB per decade. That means at omega equals to 1, its value is minus 8. So at omega equals to 10, its value will be minus 28. So let's suppose this value is minus 28. So at omega equals to 10, it should reach somewhere here, but we will not extend it for omega greater than 5. Because at omega equals to 5, we have this another line number 4 effect. So we will just stop it at omega equals to 5. So okay, so this green line is basically the resultant of line 1 and 2 for omega less than 5 radians per second. Okay, with this slope. Now, after omega for omega greater than 5 and less than 10, that means between this range, I have this additional line, line number 4, which has a slope of minus 40 dB per decade. Now the effect of this to our green line or the resultant line will be that this green line is already with a negative slope of minus 20. So when you add another line of minus 40 dB per decade rate, so the resultant rate will be minus 40 and minus 20 will be minus 60 dB per decade. That means the resultant between 5 to 10 omega will be more steeper than this minus 40 dB per decade. So let's draw this very in a cautious manner. Okay, in this range. Okay. So this value we had shifted. I think we are not sure about the value of h at this point at omega equals to 5. So let's see what we can do. Okay, what we can do here now is yes, we take the advantage of being 5 here. So when we say the slope is minus 20 dB per decade, that means for every 10 radians per second, the value of h is reduced to 20 dBs. So I think we can approximate that for every 5 for a factor of 5, this rate should reduce to minus 10 dBs. So when at omega equals to 1, it is minus 8. So at omega equals to 5, it should go to minus 18, roughly about there. Okay. So if at omega equals to 5, it's at minus 18 dB, then draw a line with a rate of minus 60 dB per decade. So this will translate that when reaching omega equals to 50, I should add more 60 dBs to minus 18. That means it should reach to about maybe minus 78 dBs. That means we further move downwards to this scale up to minus 78. Let's suppose this is minus 78. So at omega equals to 50, I should have reached to here. So something like this. But we will only draw this line up to omega equals to 10 because we have a 0. Line number 3 is coming into play. So this slope is basically minus 60 dB per decade, right? Or what else we can do to draw this line is that we just draw a line of minus 60 dB per decade at here, okay, and then just shift that slope line downwards up until here without knowing the fact that whether it's minus 18 or not. So let's suppose we do not calculate this value, and all right, so uh, let's draw a line with a slope of minus 60 dB per decade at starting from omega equals to 5. So at omega equals to 50, I should reach to minus 60 dBs, which will be somewhere here. So I should reach here. So I will draw a line like this, a slope like this. All right, and just simply draw a parallel line starting from this point. Okay, starting from here, parallel to this green line, because this the slope is minus 60 dB per decade. Okay, starting from this red dot. So just draw a parallel line until omega equals to 10. It's not parallel. Obviously, you guys will be using the ruler to make things more uh, clear. So we call this line as with a rate of minus 60 dB per decade. All right, and then just remove this line. All right, so after reaching omega equals to 10, and we have this line number 3 into action, which has a slope of positive 20 dB per decade. So the effect of this line to our original resultant line is to reduce its negative slope to from minus 60 dB to minus 40 dB per decade. So we have already draw this line here, which is line number 4 with the slope of minus 40 dB. So the resultant will be after omega equals to 10 will be the resultant line will be in parallel to this line number 4. Okay, something like this. This is you guys need to mention the slope. Okay, now what is the slope here? Like minus 20, minus 60, and minus 40 dB per decade. So this green line is now your resultant line of resultant frequency response of the given transfer function. Let's verify the answer using. Okay, so this is the magnitude plot here. So at omega equals to 5, the slope changes to minus 60, and at 10, it's to minus 40. This is what we have done. Okay. How to construct the Bode plot? Let's try another one, which is, let's try this one, which is practice problem 14.4. In this case, h of omega is 50 j omega over j omega plus 4 into j omega plus 10 squared. Again, we need to obtain the standard form, which is given as like this. So the value of k will be if 0.125 j omega, and we have a pole at omega equals to 4 and repeated poles at omega equals 10 because it's squared. So again, we see that there are more poles than the zeros. So the slope will go somewhere on the negative side of the vertical axis. So let's see. So first, find out the HDB equation, which is 20 log of h omega magnitude. This is 20 log of k, which is 0.125 plus 20 log of j omega minus 20 log of so the value of 20 log of 0.125 is approximately coming out to be minus 18.06. We can approximate it to minus 18 dBs. Okay, and the rest of the factors will be plotted directly from the table. Let's draw. Uh, First, check out where are the poles and zeros. So we have a zero crossing. We have a zero at uh, which is crossing omega equals to 1, and a pole at omega equals 4, and two repeated poles at omega equals 10. And a constant line at minus 18 dB. So let's draw the constant line first at minus 18 dBs. Let's call this line number 1. And then let's move to this j omega, which is 0 crossing omega equals to 1. So let's say this is 1, this is 10, this is 100. So this is a 0, so this is go with the upward slope. So at reaching omega equals 10, the value should reach to plus 20 dBs. I have 2 points here, and we combine these two. Okay, so let's call this line number 2, the slope of positive 20 dB per decade. All right. Next are the poles, which are starting at omega equals to 4 and 10. So let's say this is omega equals 4, and this is going to be at the rate of minus 20 dB per decade. So let's mention 40 radians as well. And let's extend the vertical axis. So this is, let's say, minus 20 dB. So it will start from omega equals to 4, and for at omega equals 40, it should go to minus 20 dB. So maybe reach it here, and we connect these points. On this line number 3, and before omega goes to 4, or for omega less than 4, the value of h is 0. And lastly, we have a repeated poles at omega equals to 10. That means the slope will be now minus 40 dB per decade. So we start from here, and after reaching 100, it should reach to minus 40 dBs. Somewhere here. Let's connect. All right. Let's mention the slope. Now we have drawn all the individual lines. We need to connect them graphically. So let's analyze for omega less than 4, in which line number 1 and 2 are uh, have some values. So again, we start with the zero crossing of this line number 2, and at this point its value is the value of h is 0. This is 0 dB, and for line number 1 its value is minus 18. So the resultant will be at minus 18 degrees, 18 dBs. So we can draw a parallel line to this line number 2, and okay, so we will be having a line which is parallel to this line number 2. So, but we also have the value of this point, which is minus 18 at omega equals to 1. So reaching at omega equals to 10, since the slope will be the same. So at reaching omega equals to 10, it should reach to my plus 18 dBs, which will be somewhere here. So we can connect these. No, sorry. At omega equals to 1, it is minus 18. So reaching at omega equals to 10, it should move to 20 dB, plus 20 dB. That means minus 18 plus 20 gives me plus 2 dB. So it should reach somewhere here. So let's connect these two lines. Okay, but we will not extend this line up to 10, but rather stop it at omega equals to 4, because after omega equals to 4, we have a line number 3 coming into action. So okay. Okay. So after omega equals to 4, I have a line number 3 into action, which is decreasing with a slope of minus 20 dB per decade. And we were increasing with a slope of positive 20 dB per decade. That means both positive and negative slopes will cancel out, and the response will be along the horizontal line up to omega equals 10. And after omega equals to 10, we have line number 4 coming into play with a slope of minus 40. So I will draw a line just parallel to this line number 4 and mention its slope, which is minus 40 dB per decade. Right. So this is the transfer function of the overall. This is the overall plot of the transfer function of the given question. And let's see the result, which is, let's see the answer. Okay, at 4 it becomes horizontal, and after 10 it goes with the steeper slope. Right, so this looks fine. Now after that, here in this example 14.5, you will see that the transfer function has some quadratic roots, and we haven't considered or discuss about the quadratic roots yet. All right, we will keep it for future. For now, we are just getting familiar with the simple poles and simple roots. Okay, so we will skip these kind of questions which contain the quadratic roots, whether in zeros or poles, for now. So let's move to the next one. This again is a quadratic one. Now, this example 14.6 says that given the Bode plot, obtain the transfer function. Now, it means that now we are given with the plot and we need to construct the or obtain the transfer function. That means reverse engineering. The process is same. That is, before we were from the transfer function, we were plotting lines, individual lines, and then adding them. And now we are having a resultant plot. So we will break this plot into individual lines. Okay. And from those individual lines, we will write their factors or write the transfer function. So let's see how to do this. Let's okay. We will break this plot into individual lines. Okay, let's see how can we do this. Okay, so okay, we need to analyze the graph first. Okay, and we need to check out these uh, points where the slope is changing, and obviously this line is extending this way and this is extending this way. We are given with the decay rates as well, and also this value of 40 dBs, and also the frequencies at which the slope is changing. So we are given with the pretty much all of the information required. So let's see how to break this whole plot into individual lines. So let's start from the left hand side first, and we can see that for the frequency for omega less than 1, I just have this this positive slope with a rate of positive 20 dB per decade, and it is reaching to 0.40 dB at omega equals to 1. And before that, it is just keep on decreasing. So how do you relate this line, this curve from the given our, you can say, useful table? We can relate that line with this one. Okay, we cannot relate that line from this one because at 0 the slope is changing, and but here in this second factor the slope is constant throughout. Okay, but the problem is this in this table this line is crossing the 0 at omega equals to 1, whereas in our case it is it it will not be crossing at omega equals to 1 because its value is 40 dB at omega equals to 1. So that means this line has a upward shift. Okay, that means uh, uh, let's draw that uh, standard slope over this graph. So we have a So this is my standard line which is crossing the omega equals to 1, and it is given as j omega in the numerator of transfer function, but it is like upward shifted by 40 dBs. That means this line contains two terms, j omega, and also a constant factor which is k. Okay, so this is supposed to be k times j omega. And how to find the value of k? We know the difference, how much it is positively shifted upwards is that uh, it's shifted from 0 to 40 dB. That means the difference is 40 dBs. And that means there should be a line which is at 40 dBs as well. Okay, so we call this 20 log of k, which is 40 dBs. So from here we can find the value of k, which comes out to be I think 100. Okay, so for omega less than 1, I have two lines. First one is this horizontal line constant k, okay, and the second one is this j omega. So I will write my transfer function. I found the value of k, which is 100, and j omega for omega less than 1. After for omega like greater than 1, the slope becomes 0. Okay, the line becomes horizontal again here. So that means at omega equals to 1, there should be a negative line or a pole with a rate of minus 20 dB per decade. Since this line was going upward with a positive slope, so there should be a negative slope at this point with a rate of minus 20 dB to make this slope horizontal. Okay, so there should be a pole at omega equals to 1, which whose line can be written as drawn as like this. Okay, and before omega equals to 1, it should have a 0 value. So we write its equation in the denominator because it's negative slope, and it's starting from omega equals to 1. So I will write 1 plus j omega over 1. So this is similar to this line here, where the value of p is 1 in our case. Okay. So now next is we see that the line is straight horizontal up to omega equals to 5. After that, we have another negative inclination of 20 dB per decade. That means there should be another pole at omega equals to 5 with a slope of minus 20 dB per decade. So I will write this pole in the denominator as well. That is 1 plus j omega over 5. And moving on, reaching omega equals to 20, I have further reduction in the slope, and the slope changes from minus 20 to minus 40. That means there will be another pole at omega equals to 20 with a slope of minus 20 dB per decade, and we include that in our equation as well. 20. So This will be the final equation or expression of the transfer function. To make it more clear, I will just simplify. Okay. So this is the result in transfer function of the given Bode plot. So let's check verify the answer. This is the final answer in h of s, where s is equals to j omega. So I have 2 5s are 10. So 100 into 100 exponent 4. J omega is s, and then s plus 1, s plus 5, and s plus 20. Okay. So this is how to construct or find the transfer function from the Bode plot. Let's try another one to make it more familiar. Let's do this practice problem. So here we have this given Bode plot, and we follow the same procedure is to split this function or plot into uh, individual lines and then write their expression. So let's figure out these changing points. And obviously this slope is extending here and it should go in this way. And the important frequencies are 5, 10, 100. All right. This looks a little bit simpler than previous because we have a lot of straight lines, horizontal lines. So I have a horizontal line for omega less than 5 at 40 dB. That means I just have a value of k. Okay, 20 log of k is 40 dB. So this will also give me, I think, value of k equals to 100. So I will write, let's draw the lines first. Okay, so this is line number 1. And then we have a positive slope of 20 dB per decade. That means there will be a 0 at omega equals to 5. So I will, this equation will be 1 plus j omega over 5. The slope is positive, so this should come into the numerator. First I have k, which is 100, and then a 0 like this. Reaching omega equals to 10, I have again a horizontal line. That means this positively going slope has an counterpart of a pole with the same rate in the negative direction. So there should be a 0, or sorry, a pole at omega equals to 10. So there should be a 0. This is line 2, this is line 3 at omega equals to 10, and slope will be minus 20 per decade. So this makes the resultant horizontal once again. After reaching omega equals to 100, I have a negative, a steeper slope of minus 40 dB per decade. That means I should have a repeated poles to make the slope minus 40 at omega equals to 100. So that means they should go like this. at a rate of minus 40 dB per decade. So let's call this line number 3 and 4, and we will write them in transfer function as in the new denominator. First is the line number 3, which is starting from omega equals to 10. The slope is minus 20 dB, so it's just like this. And for line number 4, I will write 1 over j omega over 100. Okay. But its slope is minus 40, so it will get squared. Right. Simply, I will just simplify this. Okay, so this is the transfer function here. Bode plot. Let's verify the answer given here. S plus 5, plus 10, S plus 100 square, and this is 2 millions. So maybe this will give me 2 millions. Okay, so this is correct. So likewise, we can do some more examples. So I will give you guys the related problems from this book for practice in this weekend. But we haven't still considered the phase plot yet, and also some questions regarding the quadratic poles, such as you guys can do these questions. You can also do this one as well. Regarding 14.4, this looks a quadratic equation, but I think this can be factorized. This can be made a complete square. Let's see. So we can write this minus as j squared or iota squared. Okay. So this will you can write it like this. So this becomes a complete square. That means we can write it as j omega plus 5 whole square. So this makes this transfer function as okay. So now we can construct the Bode plot using the techniques we have already covered. So in case of quadratic roots or quadratic equations, we first need to check whether we can complete the square or not. If we can complete the square, that means we can do it. But if not, we skip for now, such as this question 14.16, in which we have this quadratic equation and we cannot complete the square. So we will skip for now. and we'll see them later. And also there are some questions in which the Bode plot is given 22, 23, and this 24, and you guys need to construct the transfer function. So that's all for today, and we will discuss the questions and queries in the upcoming lecture.